Hi, in this module I will introduce beams. A beam is a component that deforms mainly by bending. A beam is subjected to a transverse load. A transverse load is a load that acts perpendicular to the longitudinal axis and or moments that try to bend it. These moments are called as bending moments. For example, consider this beam A, B, C, D. Due to the application of this transverse load F, the beam has got bent. Similarly, consider this another beam which is subjected to moments M on the ends. Due to this moment M, the beam has got bent. So, this moment M is called as bending moment. Now, to carry this load F, supports are provided on the beam. So, these are the supports which are provided on the beam. These supports are grounded. Beams are classified according to the types of supports. The first is simply supported beam. A simply supported beam is that which is supported on simple support on one end and roller support on the other end. So this is a simple support and this is a roller support. A simple support is also called as a pin support or a hinge support. A simple support is the support from which reactions are forces in vertical and horizontal directions. It does not give moment reactions. That is, the reactions from the support are only the horizontal force Rx and the vertical force Ry. It does not give any moment reaction. Similarly, a roller support is the support from which reactions are forces in vertical direction. It does not give moment reaction and any reaction force in horizontal direction. Therefore, from a roller support, we have only one reaction, that is reaction in Y direction. Next is a cantilever beam, a beam that is fixed on one end and free on the other end. So this beam is free on one end and fixed on this end. So it is a cantilever beam. A fixed support is the support from which reactions are forces and moments. So from fixed support we have horizontal reaction, vertical reaction and also a moment reaction. So due to this moment M, it will not allow beam to bend at the fixed support. For example, if a load P is applied on this beam, then it will bend in this manner. That is, it can be seen that at the end the beam is straight, it has not bent due to the reaction M1. Propped cantilever beam, a beam that is fixed on one end and roller supported on the other end. So this roller support provides an extra reaction to this cantilever beam. The extra reaction is Ry. A fixed beam is a beam that is fixed on both ends. So this beam is fixed on both the ends. Overhanging beam, a beam that has overhangs on ends. So this beam has these overhangs on either side. So it is an overhanging beam. Now we have seen that loadings on the beam are either the transverse load or a direct moment M. These loads can be applied either as a point load or as a distributed load. A point load, also called as a concentrated load, is the load that is assumed to act at a point. It can be a point force or a point moment. For example, P1 and P2 are point forces because they are acting at points on the beam. Point moment, this M is a point moment because it is acting at a point, that is on the free section of this cantilever beam. All these are point moments because they are acting at a point. Distributed load, a load that is assumed to act over finite area. It can be uniformly distributed, which is called as UDL, or varying distributed load, which is called as VDL. For example, this distribution is a UDL because you can see that the intensity of this load is equal everywhere. Here, at all the points, the intensity is this magnitude, which is same. So it is a uniformly distributed load. A uniformly distributed load is specified by mentioning the intensity at a point, which is expressed as W in Newton per meter. Another is varying distributed load. A varying distributed load is that load whose intensity is varying along the length of the beam. As it can be seen, this load has a zero intensity at this end, but it has maximum intensity at this end, and the intensity at this point is different from this point, is different from this point. So it is a variably distributed load. A variably distributed load is specified by mentioning the maximum intensity, which is this W naught as Newton per meter. The first step in the analysis of the beam is to find the reactions that are given by the supports on beams. Support reactions can be found by force balance and moment balance. Since the beam is in equilibrium, therefore net force on the beam in any direction, either horizontal direction or vertical direction, must be zero at all points on the beam. Similarly, since beam is not rotating about any point, therefore the net moment must be zero at all points on the beam. To find the reactions given by the support, replace the supports by the reactions that are given by them. For example, a roller support gives only a vertical reaction. Therefore, replace the roller support by a vertical reaction like this. Let this vertical reaction be RB. This end is B and this end is A. Similarly, a simple support at end A can be replaced by a vertical reaction at A, because a simple support also does not give any moment reaction. So we replace this by a vertical reaction RA. The horizontal reaction is not useful because it is RAX, which will be RAX equal to 0, because the net force on this beam is RAX, which must be 0 because this beam is not moving in the X direction. So we can say here that RA plus RB, considering positive Y to be upwards, minus the force due to this UDL. The force due to this UDL can be written as its intensity W into the length of the beam L, that is WL, because W is Newton per meter. So over a length L, the total load acting will be W into L. Now this net force RA plus RB minus WL must be 0, because this beam is not moving in the Y direction. This WL is taken negative because it is acting in the minus Y direction. Now we can also balance moments about any point on this beam, either point A or point B or point C or point D or any point on the beam, because this beam is not rotating about any point. Let us do the moment balance about point A. Remember that this length is L, and this reaction is RB, this reaction is RA. So we can write RB into length L. This moment of RB is in anti-clockwise direction about point A. So we take this as positive. We will assume that counterclockwise moments will be positive. The moment of RA about point A will be 0 because RA is passing through point A. Now, for the purpose of calculating moments, the UDL can be assumed to be acting at a point. So we can replace this entire UDL to be acting at its center, that is at a distance of L by 2 from end A. So the moment of this WL at point A will be WL, that is load into distance, which is L by 2. Now since this moment is trying to rotate the beam in clockwise direction about point A, therefore we will take this as negative because we have assumed counterclockwise as positive. This is the net moment at point A. This net moment must be equal to 0 because this beam is not rotating at point A. So from here we get RB is equal to WL by 2. We have already found that RA plus RB minus WL is 0. So putting here the value of RB, we can get RA WL by 2 minus WL is equal to 0. So we can get RA as WL by 2. So we have found the reactions RA and RB which are given by these supports on the beam by force balance, that is this equation, and moment balance, that is this equation. Take another example. This is a cantilever beam on which a point load P1 and a point moment M0 are acting. We want to find the reactions given by this fixed support. So the first step is to replace this support with the reactions that it can give. A fixed support can give a reaction in X direction, Y direction, as well as a moment reaction. So we have replaced the fixed support by the reaction RA, which is in vertical direction, and the moment MA. The reaction in X direction, which is RAX, will be equal to 0 because there is no horizontal forces acting on this beam. Now assuming this to be positive Y, we can write force balance as RA minus P1 is equal to 0 because there are only two forces acting in vertical direction. Therefore from this we can get RA as equal to P1. Let us do moment balance about point A. At point A, the moment of RA is 0 because RA is passing through point A. The moment of P1 about RA is P1 into L1. Now since this moment P1 into L1 is trying to rotate the beam in clockwise direction about point A, therefore we will take this as negative, assuming that counterclockwise is positive. This M0 is trying to rotate the beam in clockwise direction, therefore we take minus M0. Now this moment MA is trying to rotate the beam in anti-clockwise direction at point A, therefore we take this as positive. This net moment on the beam at point A must be equal to 0 because this beam is not rotating about point A. Therefore we get MA is equal to M0 plus P1 into L1. So we have found the reactions given by this fixed support on the beam, that is RA and MA, by force balance and moment balance. Now let us see what are the effects of these loads on the beam, that is what are the internal forces and internal moments on the cross sections of beam due to applied loads. Consider this cantilever beam on which a load P1 is acting. In 3 dimensions, this beam can be shown like this. To know about the internal forces and internal moments on cross section of the beam, we have to make an imaginary cut on this beam like this. On 3 dimension, this cut will be on the cross section like this. So we have made an imaginary cut on this beam in 3 dimension. This cut will be like this. Now, since the beam is in equilibrium, therefore this part of the beam, that is this part of the beam, must also be in equilibrium. To maintain the equilibrium, internal forces will be acting on this cross section, that is on this cross section. There are 2 types of internal forces that will be acting on this cross section to balance the applied load P1. The first one is a shear force. So a shear force V will be acting on this cross section to balance the applied load P1, so that this part of the beam can remain in equilibrium in vertical direction. So V minus P1 will be equal to 0. That is V, that is shear force in this case, will be equal to P1. This V is shear force because it is acting parallel to cross section A, B, C, D. The other reaction that will be acting on the cross section is the bending moment. Let this length be L1 and this load is P1. Now this load P1 is giving a moment of P1 into L1 about this axis. Let us call this axis as Z axis. So this P1 into L1 is the external moment that is acting on the cross section A, B, C, D. To balance this external moment, an equal and opposite internal bending moment must be acting on the cross section A, B, C, D. Now this external moment P1 L1 is trying to rotate the element in clockwise direction. Therefore the internal moment on the cross section ABCD must be acting in anti-clockwise direction. So this is MZ, that is internal moment to oppose this external moment P1 L1. So the moment of load P1 on this cross section will be P1 into L1. On this cross section it will be P1 into L2. Because of these moments, this beam will bend in this manner. To resist this bending, internal forces will be acting on every cross section. So if we make a cut on any cross section, we can see that an internal bending moment MZ will be acting to oppose the external bending moment P1 into L1. An equal and opposite will be acting on this cross section. Take another example. In this cantilever beam, 2 loads P1 and P2 are acting, and we want to find what is the reaction on this cross section. So we make an imaginary cut. We can see that to maintain the balance, the internal forces on this cross section must be a shear force V and an internal bending moment MZ to oppose the moments given by P2 and P1. This V, that is shear force on this cross section, must be equal to P1 plus P2, but must be acting opposite to P1 and P2. That is, it is acting in upwards direction. Similarly, the moment of P1 on section XX is P1 into L1, and the moment of P2 is P2 into L2. Therefore, the internal bending moment MZ on the cross section XX must be acting equal in magnitude to P1 L1 plus P2 L2, but its direction must be opposite to that of external moments P1 L1 and P2 L2. Since P1 L1 and P2 L2 are acting in clockwise direction about cross section X, therefore MZ must act in anti-clockwise direction about cross section X. So we have seen that when loads are applied on the beam, that is transverse loads and bending moments, then internal forces are generated on all the cross sections. These internal forces are a shear force V and an internal bending moment Mz. This ends this module. Thank you.